So we want to prove that X is equal to U lambda V transpose, and X is SVD of X. V is V1 to V2, R, and N minus R. And C star is a family of solutions because B could be anything. Because B could be, this one could be any matrix. We want to prove that C star, the weights that you want to solve, is V1 transpose plus V2. So it's not unique because B could be a family of solutions. BB could be any matrix, and so C star could be a family of solutions. So the proof is very simple. For example, recall from linear algebra that if AX is equal to B, then if a solution exists, so I mean if a solution X is X0 plus V, where if X0 is a solution, okay, so you can add any elements of the kernel to that solution. So if V is inside the kernel of A, so all of these are solutions. So any member of kernel that you add to your solution is a still solution. And it is obvious. And so we can write C as V1 transpose. And so this is one solution, which was X0. And we need a basis for kernel because we want to say any vector in kernel is also a solution. So a good basis is your V2. V2 is here. This is SVD and V is this, and you get the second part, which has N by N minus R. And you multiply V2 by A, which is N minus R times N. So overall it is N by N. And this is N by N. And this is N by N. So you can write this as V1, V2, V1 transpose A. So this is N by N, this is N by N. And because this one is orthogonal and therefore full rank, and so all optimal solutions are such that rank of C is equal to R, so A is equal to B V1 transpose. And that is the proof. So let's talk about nuclear norm. You know, the nuclear norm is just the sum of its singular values. So the theory goes on, and you want to minimize. So instead of rank, you want to minimize the nuclear norm subject to X is equal to XC. After finding C, you know, we need to find an affinity matrix, because in spectral clustering that I will explain in the future lectures, in spectral clustering, it says that give me an affinity matrix. What is your affinity matrix? We say, okay, we have calculated the affinity matrix is just V1 transpose. And that's it, because if I will explain that in the few future lectures that X transpose LX, for example, L is your Laplacian, this one is positive definite and can be written as omega ij. These are similarities affinity in the affinity matrix, and xi minus xj squared, and this should be non-negative. So it is always positive definite. A matrix times its transpose, this one. So we use the trick that a matrix times its transpose is always positive definite. So we are sure that there is no problem with the affinity matrix because it is positive definite. We have carefully chosen the affinity matrix such that it becomes positive definite because a matrix times its transpose is positive definite. And so until now we have talked about sparse clustering, but low rank sparse clustering. Low rank sparse clustering. But in reality, you know that data is noisy, and you have to care about. You also should make it robust, like robust PCA concept, robust everything concept, and that's why the motivation for sparse subspace clustering comes in. Sparse subspace clustering. So now we want to minimize the L0 norm. The few elements that represent. But the problem with this is that this L0 norm is not robust. Is not robust to noise. And also, these kind of norms leads to combinatorial, because which set do you want to choose? So it's completely combinatorial and is useful for computer scientists. But in machine learning, we want to simplify things as much as possible. We don't want to talk about combinatorics and those things because it takes time. And it is very hard. The problem is hard. It's hard to find good algorithm and prove that is the best. And both time and space complexity is efficient. That's why instead of that, we relax the problem. So we use convex relaxation and say instead of L0 norm, we want to minimize L1 norm. Again, subject to x is equal to xc. This is more efficient because x is a d by n matrix, and c is inside Rn. Because this is small c, but for the big C it is, so C is C1, C2, Cn, because we have to do it for all points. So this is C and this is n by n, but each of this is n by 1. But we have n points, that's why it becomes n by n. So it is an underdetermined linear system of equations, and of course this is the assumption that Cjj is equal to, you cannot write each point in terms of itself. So What we want to do is that you want to write each point in terms of other points, y1, yn, and then ci1, ci2, cin, and this is ci. And this is your dictionary, you know. The problem with this algorithm is that you have to solve n times. For example, in future, I will show you that you have to solve ADMM method n times. And so the size of your dictionary is too big. That's why recent algorithm, after 2019, I have seen that some people use simple dictionaries. So they use multiple dictionaries. So naturally, it is a generalization of this paradigm, because instead of a very big dictionary Y, we select some sub-dictionaries so that the computational complexity reduces. So in general, Y is in space of dictionaries. And I mean, this is my intuition that I want the Frobenius norm of dictionary between something. This is really interesting for me. And you can talk about multi-resolution way of handling this problem. Of course, I haven't seen any article on this area, because you are trying to generalize sparse subspice clustering. So in practice, solving NL1 minimization problem, you know, you have to solve NL1 minimization problem, because for any point you have to write it as a linear combination of other points. So that's not practical. That's not tractable, of course. And scalable sparse subspace clustering by orthogonal matching pursuit can be one approach. The other approach is Oracle-based active set algorithm for scalable elastic net subspace clustering. This was the name of another article. And so you got the point that you need to solve a system of equations n times. So in other words, I can say that sparse subspace clustering is equivalent to all recovery algorithm. Any recovery algorithm in compressive sensing is equivalent to that. And the recovery algorithms, recovery algorithm, in general, there are sequential methods such as matching pursuit, such as orthogonal matching pursuit, such as co-samp. I mean, this is the correlation of many columns with I. This is the idea. And of course, you can use joint recovery methods. So these methods are not sequential, such as focus methods, such as basis pursuit, such as lasso, such as Dantzig selector. There are many methods. But let's talk about matching pursuit, for example. In matching pursuit, we want to solve the problem is all of them is just AX is equal to B, and we want to approximate it as find a solution. And you know that it is equivalent to compressive sensing equation, compressive sensing problem. So we start by finding the atom that best matches AX to B. Then we sweep over all columns of A to see the best match between AX and B. And let's go greedy, and the resulting algorithm, the resulting column will stay with us, and we wait for the second atom to join it. And the solution grows the support one item at a time. But the orthogonal matching pursuit is that AXK is not B, and we do recurrently. So at current residual, R is residual, is B minus AXK. So we use this residual to choose the next atom. So the algorithm is that we first initialize K is equal to 0, X0 is equal to 0, R0 is B minus AX0 is equal to B, and at the start of the algorithm we have nothing. We have not selected anything. We compute E of I, which is a minimum of ZAI minus RK minus 1 squared. Then we choose the index, the index is between 1 and M, such that E of I0 is less than E of I. Now we update it. We say that, okay, we had SK minus 1. We, like submodular maximization, you add something to that. Now we add an index to that. And then we use the least square and then find XK is minimum of AX minus B. Of course, subject to support of X is SK till now, because S is getting S is growing, and finally we update residual. RK is B minus AXK. Step 1 is very easy, because you just need to find that AA transpose ZA minus RK minus 1 is equal to 0, and you get the optimum point. I transpose RK by 1, I transpose AI, and this is 1, and so it becomes AI transpose RK minus 1. So instead of minimizing AI, we maximize AI transpose RK minus 1. So the low-rank subspace clustering, in low-rank subspace clustering, we wanted to minimize the nuclear norm, subject to X is equal to XC, and the answer was that V1 transpose, where V is just the right singular vectors of U sigma V. So unfortunately, there is no theorem for noisy data. That's why that is the motivation for sparse subspace clustering. So we minimize L1 norm, subject to, again, X is equal to XC, and diagonal of C should be 0, because no points should be written in terms of its own, in terms of its own. And unfortunately, we don't have any closed form. Unlike the previous algorithm, with which we had a closed form, But now we should solve n different ADMM. So we should distribute it to n different machines and solve for each point. We should solve a different